Hello everyone, welcome to today's discussion session. Uh, so I will be discussing few problems on Riemann integral today. Uh, so I will start with some questions, uh, one or two questions with differentiability of function, and then I will move on to discuss Riemann integral. Then we will also discuss Riemann still just integral. Uh, yeah, so that's the plan today. So in between, if you find any argument difficult to understand, you can raise your hand, ask questions. A recording of these studies will be available by tomorrow. Um, so, without a further delay, let's start today's discussion. So, let me formally introduce myself to you. I'm Prerak. I'm from Aizer Bhopal, and this is another live session discussion with you guys. A recording of this session will be available to you on my YouTube channel. Uh, Previous recording, you can also go through my YouTube channel. All the recordings are available on this channel. uh, in which you might be watching now. Okay, um, so let's discuss some questions. Okay, so this first question is about differentiability. So suppose f is a differentiable function at c, and that f of c is equal to 0. Now we need to show that g of x is, which is defined to be modulus of fx. Uh, we need to show that this gx is differentiable at c if and only if f prime of c is equal to 0. Okay, so uh, we will, uh, yeah, so in this statement, as you know, that is it's another if and only if statement. Okay, so how do we understand this if and only if statement? So we say that first we need to prove, let me write it as A, that uh, assume that gx, which is defined to be modulus of fx, is differentiable at c. Then you need to prove that f prime of c is equal to 0. Okay, and the second statement that you need to prove, that you assume that f of prime is equal to 0, then g of x, which is equal to g of x, which is equal to modulus of fx, is differentiable at c. Okay, so this is the question. So this if and only if statement can be uh, reduced to the questions A and B type, where we assume the first statement and then we prove the other side, and we assume the other as assumption and prove the uh, first half. So I will prove first A and then I will prove the B part. Is this uh, fine? I've just rewritten this if and only if statement as two statements independently, and I will prove each of the statement, and it is equivalent to prove that the whatever asked in the question. So I will assume that gx is differentiable at c, and then I will prove that f of prime is equal to 0. So I start with proving A. So what are the given details? So we are given that uh, first is f of c is equal to 0. Okay. Second, f is differentiable at c. Third, we have given f. Uh, Third, we have given that g, which is mod f, is also differentiable at c. Okay, and we need to prove that uh, that f prime of C is equal to 0. Okay, so we assume that case 1, let's say case A, uh, suppose if it is positive, okay, suppose so we also assume that it is non-zero, and then we will arrive to some contradiction. Okay, so suppose if it is f prime of C is positive, okay, f prime of C is positive, and f of C is 0. So if I draw the graph near the C, near point C, so let's say this is the graph, okay, and this is the point C, and if I try to draw it locally, since its slope is, I'm drawing the graph of function f, okay, and it is given that at C the slope of the function is positive. So positive slope means it needs to be locally be like this, okay, something like this. It can't be a graph which is like this, okay, which has negative slope. So it needs to have a positive slope at this thing, okay. And further, because yeah, and we know that this condition, this second condition also implies that f is continuous at C. Correct? F is continuous at C. And we are also assuming that this limit is positive. So what does this mean? That limit as h tends to 0, f of C plus h minus f of C divided by h is positive. Okay. So basically, when you are near, if you take any neighborhood of this C, the slope is positive. That means the difference between uh, this point and the point at C, this difference divided by h is positive. Okay, and if you take h to be negative, okay, basically if you go backwards, then this difference is going to be negative. So in some sense, locally, what you are capturing is that in a small neighborhood, this quantity is positive. Basically, this represents that locally means around a neighborhood of C, there exists a small neighborhood of C. So if I rewrite it, so what does this limit means? This limit simply means that uh, there is some epsilon greater than 0, such that for h small enough delta, which is small to delta, such that there exists some delta, such that this quantity is smaller than epsilon. Okay, this is what it means. In particular, I can take this h this side. Okay, so this quantity is 0. So uh, so if I assume that this quantity is some f prime of C, and if I subtract this quantity with this, so in particular what I'm saying is, yeah, so if I subtract this, so then the limit will be 0. So that means f of C plus h minus f of C minus h times f prime of C. This is smaller than epsilon times this thing. Okay. Yes. So what it means that yes. So this quantity, this difference with this quantity is smaller than epsilon, and this epsilon is true for any epsilon. So it is getting closer to closer. So in some neighborhood, so this difference is getting close to 0. Okay. This difference is getting closer to f prime of C, which is the definition of this. Okay. If I come back to the what I am trying to convey is, so So what I'm trying to convey, locally, because this I'm assuming this to be positive, so around a point C there exists some h greater than 0, such that in that C minus h plus C plus h, the slope, the function f of x, uh, locally looks like this. Okay, it's increasing. It looks like this thing. So in other words, if I so if yeah, so if I travel from the right hand side, if I approach C from the right hand side, this, yeah, if I approach from the right hand side, this f of x uh, is positive for some x small enough to this neighborhood, x minus delta, x plus delta. And similarly, if I travel from the right hand side, sorry, C plus delta. And similarly, this will be negative. So in particular, if I take the g of x, so g of x will be locally be like this type of function. If I take g of x, which is nothing but going to be the modulus of fx, so it's going to break the differentiability. G is not differentiable. So what I'm giving is more intuitive idea to solve this question. This may not be the exact proof of the question. Similarly, if I assume that f prime of C to be negative, then the same argument can be given. Locally, the slope at this point at C, the slope may look like this. And again, the function gx, if I take, which will be the modulus, it will again be uh, like this. Okay, so again, it will lose the differentiability at C. So in both cases, we arrive to a contradiction. So it implies this will be our case P. So it implies that f prime of C has to be equal to 0. Okay, now we prove the part B. Okay, in part B, we assume, so in part B, we assume that f of prime is equal to f of prime of C is equal to 0. Okay, we assume this part, that f of prime of C is equal to 0. Then we need to prove then g of x, which is nothing but modulus of fx, is differentiable at C. Okay, so again, pictorially, if I try to see this, uh, this is my point C. Okay, this is point C, and now f of C is 0, so that's why it is lying on the axis. Function will be uh, function graph of the function will go through this point at C. Okay, it will pass this point. Um, okay, and now the second assumption is that f of prime is also equal to 0. So when does f of prime is equal to 0? F is a differentiable function. Okay, so when does f of prime is equal to 0? So there are only three cases when this thing is happen, when it goes like this and comes back like this, or in the reverse way. Okay. So these are the three possibilities. Now in this possibility, function is now there is another possibility when uh, this thing happens. Okay, at C, because the slope is parallel to the x-axis. So this is another possibility. So in both of the case, in the first case, this case, in both of the first case, my gx function. So in these two cases, above my function is positive, below my function is negative. Okay, above is the plus y-axis, below is the negative y-axis, and similarly in this case also. So in this case, gx will be minus of fx, and in this case, gx will be fx. And in this case, my gx will be 0. Okay, my gx will be 0 for some small neighborhood of C. For some small neighborhood of C. Yes. So in this case, G will always be because G is nothing but f of x, and f of x will be 0 for some small neighborhood of C. So Gx will be 0. So Gx is differentiable at C. And now in this case, in the first case, it will be Gx will be either equal to minus fx. In the second case, it will be fx. So in both of the cases, it will be differentiable at C, because f is differentiable at C given to us. So I have given what is being asked. Okay. Um, it's not the explicit proof you might be looking for, but it is an intuitive proof how the understanding of graph of a function and the understanding of a differential of the function as a slope helps you to uh, solve such kind of questions, because differentiability and continuity are both local phenomena. Okay, local phenomena means you only need to understand behavior of the function in a small enough neighborhood of the point. Okay, that's what we have done in this in these cases. So now now we move on to questions based on the the Riemann integration. So in the last session also I have discussed a few problems on Riemann integration. There I discussed the definition of the Riemann integration as well. So today, if needed, I may recall the definition if it's if any one of you uh, want to know the definition, want to recall the definition, then I may recall the definition. Otherwise, I will not prefer to do so. So this question number two, which you can see on the screen right now. In this question, we have given a function which is a bounded variation. Okay, so they actually introduced the definition of the bounded variation in this question. Uh, this question is from your assignment, so you might have seen this question as well. Uh, so it is a bounded variation function. Okay. So when do we say it is a bounded variation? So if there exists a constant k which is positive, such that this inequality holds for any partition of the closed interval AB. Now now we need to find out which of the following statement is true or false. Which of the following statement is true for the function, for such function on AB? So first option says that every Riemann integrable function has a bounded variation. So this is not true. You can find examples of so not this is false. So this is false. You can find examples. There are examples. Uh, example of a bounded variation. Sorry, there are example of Riemann integral function that are not bounded variation. Okay, so there are examples of such functions. I might have one of the example. Um, so the example for counter example for option A. If you take this function fx to be x times 1 over sine x, okay, for x being non-zero and 0 when x is 0. So this function, uh, this is, so first we claim that number one, that f is Riemann integral on 0 comma 1, let's say, okay, on this closed interval 0 comma 1. So f belongs to Riemann integral was this thing, and the second is that f is not a bounded variation. Okay, so f is the Riemann integral is uh, because of this, because this sine 1 over x, sine is a bounded function, so it bounds in this domain. You can say it is bounded between 0 comma 1, correct? And now okay, and now if you multiply it by x, so you can say that this function is bounded by uh, 0 and x function. So the integral of this function on this domain, because both of the, because this integral is nothing but a limit, and uh, this limit is bounded by two limits, by limits of two functions, which is on the top and which is on the bottom. So by sandwich, this limit also exists. Okay, uh, so this limit, so basically what is Riemann integral? Riemann integral is the limit of the Riemann sum. Okay, and this Riemann sum, can you can think of it is bounded by this function and that function, and this limit will exist because the bounding functions, limit of the bounding functions exist. So this is a Riemann integral function, but uh, this is not an bounded variation. Uh, and to say that why it is not a bounded variation, so this is true. And now in order to say that why it is not an bounded variation, not a bounded variation, you need to take a specific interval. Okay, so you know, to take a specific you need to take a specific sequence. Take xn to be 1 over n pi plus pi by 2. Okay, if you take this uh, partition, if you take this partition of your interval 0 comma 1, if you take this partition, then the problem will occur, because uh, because what happens is that sine of value of sine at these points, okay, sine 1 over xn it will be just sine of n pi plus pi by 2. Okay, so depending on the value of n, if it is even or if it is odd, so it will take signs. Okay, if it is even, it will take plus 1. If n even, it will be minus 1 if n is odd. Okay, so uh, so what will happen if you consider this sum of f of xi minus f of xi plus 1 type sum, this sum if you consider, so sine 1 over xi minus xi plus 1 times sine 1 over xi plus 1. Okay, so uh, then what will happen, it will be then sum both of the xi's, because this sine 1 over xi will either be negative or will be positive. So if it is positive, then the alternate one, alternate endpoint. Okay, so one of the endpoint will be either even or odd. Okay, if one endpoint is even, then the other endpoint has to be odd. Okay, so with that, and on so on either of the endpoints, sine takes plus minus one value. So it will sum all these xi's. Okay, so in particular, it will sum up these things, and this will sum will go from some 0 to m, which will partition the set. Okay, and now this quantity depends on the depends on n. Okay, number of partition you are choosing. So this quantity can be made as large as you want. Okay, so if you say that you are bounding it by k, then you can find some natural number n which is larger than k, and you use that n to partition this set. You do that, those many partition, take that value here, and this sum will be then larger than this k. So you cannot bound for given any constant k. You can always partition your set uh, uh, in such a way that this sum will not be bounded by that k. So this proves that uh, that if a function is Riemann integral, it need not to be a bounded variation. Okay. Okay. So if this so this statement is false. Now, what is the second statement? Second statement says that every function having bounded variation is Riemann integrable, but may not be bounded. So we will show that every bounded variation is bounded. Okay, bounded variation implies bounded function. So we will show that. Okay, so let us show that. So for to make B false, so what is B? B is uh, every bounded variation is not bounded. Okay, so we will show that this is false by proving that it is bounded indeed. Okay, so so for bounded, so we say um, a function on an interval is bounded if f of x, okay, the modulus of f of x is smaller than some, if there exists some constant, let's say k naught in R, such that this is smaller than k naught. Okay, so then we say that the function is bounded. So how do we prove this? So we take uh, Yeah. So if I take no partition of the set, if I take the x0 to be A, x1 to be B, then what happens? Then we see that f of A minus f of B is smaller than K. Okay, correct? By the definition of the bounded variation. So, so this, and now what is f of A minus f of B? F of A minus f of B plus f of B. Okay. So what I'm saying is uh, that f of A and f of B are both finite. Okay, because if any of them is not finite, then this their difference can't be okay. Then if any of them is not finite, okay, they are uh, this this difference can't be bounded by some k. Okay, so basically this f of A and f of B are both real numbers. They exist on this real number. Okay, so f of A and f of B are both real numbers, so they have to be from finite quantity. It is not that they are, it's an infinite quantity. It exists on the real line number, so they are both finite. Okay, so basically what I can do now, I can take another partition of AB. Okay, so partition AB as a point in between x, where x is any point between a b interval. Okay, so if I consider this partition, so in this partition by definition I will get this thing plus f of x minus f of b. Okay, so now this quantity is obviously smaller than this quantity. Okay, the only, if I take consider the only first part, then this must be smaller than this. And now further, if I think of this quantity f of a minus f of x, if I sum both side by f of a, correct? If I sum both side f of k, then this quantity on the left hand side is nothing but, by triangle inequality, larger than the fx, mod of fx. And the quantity on the right hand side, this quantity is a constant, so we call this to be k naught. Okay, this is a constant, we call this k naught. So in particular, we have shown that f mod of fx is smaller than k naught, and our choice of x was arbitrary. So it shows that the function f is bounded, correct? So yeah, um, so this completes this completes the proof that b is also false statement. Okay, now we come to part C, which says that every function having bounded variation is bounded. We have proved that part. And now we also it also says that it is also Riemann integral. We need to prove this second part, that bounded variation function which is bounded variation is also uh, Riemann integrable. Okay. So C, um, okay, F is bounded variation implies F is Riemann integrable. So what is the definition of Riemann integral? integrable. So in that definition, we say we define two upper sum and lower sum. Okay. Um, so I will be using this definition that which involves upper sum and lower sum. For Riemann integrable, there is another definition which is also equivalent to this, where we define Riemann sum and then we take the limit of the Riemann sum. I will be using the equivalent definition, which involves upper sum and lower sum. You approximate your function from the upper, you define the upper integral and you define the lower integral, and you look at the limit differences of them as uh, as your partition takes uh, as your radius of the partition tends to zero. So um, yeah, so upper sum is defined to be uh, this maximum. Okay, so let's say this is the partition uh, A, then x, which is equal to x naught, x1, xi, then xn, which is also equal to b. Each of the xi belongs to this closed interval a comma b. Okay, so this is the partition I'm considering of interval a b. Now in this partition, um, yeah. So now if I talk about UFP, which is the upper sum of this, so we take the uh, maximum of the function in that interval, in that subinterval, times the length of the interval from I to I equal to 1 to n, correct? Similarly, the lower sum, where I take the minimum and the length goes as same, I from varying to 1 to n, correct? Okay, so in order to show that it is Riemann integrable, we need to show that for every epsilon greater than 0, there exists some delta such that the there exists delta uh, there exists a partition whose there is a partition and delta whose such that the radius of partition is smaller than delta, and that the radius of partition is smaller than delta, then the difference of UFP minus LFP is smaller than epsilon. Okay, so how do we achieve such a partition whose length is smaller than delta? That is the question. So first we take a partition. Um, yeah, we can take our partition to be as small as we want uh, by breaking our interval into uniformly subintervals, and those uniformly subintervals of length n. So what I'm saying is, given any interval AB, okay, A and B, you can break your interval into uniform length subintervals. And how do you find that uniform subinterval? That uniform subinterval is nothing but B minus A difference divided by the number of subintervals you want to make. So if I want to make n subintervals, so I will divide it by n. Now what you need to do, you just need to add A plus this quantity, and now this will be your first x1. X2 will be A plus 2 times the difference, and so on and so forth. And as xn will be A times n times this divided by n, which is nothing but equal to b. Okay, so this is how you create this subinterval, uh, and you can take this n to be in such a way, you can take n to be that large so that it is smaller than a delta. So in particular, you can uh, choose n such that this is smaller than delta. Okay, Okay, so um, yeah, so in that case, if I consider such type of partition, so my definition of UFP can further be simplified because the difference will be then constant. Okay, so you can take that difference outside the integral. So this will come out similarly, uh, small I. And since we are interested in the difference of the upper and the lower sum, we do the difference. So if I do the difference, what I get b minus a because that is a common term. Summation from 1 to n, mi minus small mi, correct? I get this term. And now, um, yeah, and now I want to somehow use the bounded variation formula. This function is not given to be continuous function. If it is given to be the continuous function, I could have these maximum and minima can be achieved by some value of xi in that interval. Okay, but it is not given to be a continuous. It is not given to be continuous function. So these mi's are not achieved by some xi in the interval. Okay, um, is not achieved by function f. So what I need to do, I need to just use the fact that mi is the supremum of fx for x sitting inside this interval. Okay, so yeah, so what happens if I so yeah, so if I subtract fx, so there is, so for n uh, there exists some xi, so there exists some ci in xi minus 1 comma this, such that if I subtract this value, or sorry, if I add this value in 1 over n value, if I add into ci, then it will be larger than mi. Okay, you can always find some ci which will this happen because mi is the supremum. Mi is the supremum. You will always be able to find out such ci. Or you can take as small as mi. You take as small as n to make this quantity large. So okay, so you take, sorry, you uh, yeah, so you take n appropriately so that this thing happens. Similarly, uh, you can also find some ci prime in this interval such that if you subtract that ci, if you subtract uh, 1 over n from this ci prime, it will be smaller than mi. Okay, so now from these two equations, what will be if I consider difference? Okay, so if I consider difference, then what will happen that this quantity will be larger. This quantity will be smaller than this quantity. Mm, okay, and then the sum 2 over n. Correct? Yeah. And in particular, if I multiply it further by v over n by n, then I had to multiply this by n. Correct? Now I choose, so I get this inequality. Okay. So if I further simplify this inequality, how can I simplify this? So it is basically f ci, uh, and further if I take the modulus of this, so it will be modulus of the right hand side, it will be larger than this previous quantity. So I can further consider this one more identity, this thing, plus 2 times b minus a divided by n square, this thing b minus a by n, correct? This further, and then I applied the uh, uh, what a triangle inequality as well. So this step, this from here to here involves two steps in between. So first I apply the modulus, and then in that modulus I apply the um, triangle inequality as well. So I get this inequality. So let's call it to be star. And further, if you sum it up, okay, you apply summation both sides. If you apply summation both sides, you will get f p. This L f p will be smaller than b minus a divided by n summation this thing 1 over 1 to m plus 2n square b minus a, which you are summing up n times. So n will come and then it will divide, it will subtract this n. So it will get 2n by n type thing, correct? And now this whole thing, now the idea is to apply the bounded variation, but you can't apply here. You need to further do one more step. So you need to choose appropriate partition in order to apply this. Okay. So how do I choose that partition? So for example, yeah. So what I have done, so I had this partition earlier. Okay. Sorry. Yeah. So I had this partition earlier, which is this is x naught, and then there is x1, and then there is xi. Okay. Uh, there is then xi minus 1 and then xi, okay, and then going in this way, then there was xn, which is b. And what we did, we found some element in between x0 and x1. Okay, we call that element to be, actually we found two elements, we call them to be c naught, sorry, c1 prime and c1. uh, I We don't know the ordering between those two, but those two will lie in this. We can order them appropriately. Okay. Similarly, here I will have Ci minus 1. Here I will have Ci, which is Ci minus 1. Assume I don't know the order between them. Uh, so I will have Ci prime. And similarly, Ci plus 1 prime, then Ci plus, and similarly Cn and Cn prime, something like this. I don't know the order, exact order between them. Okay, so this thing and this summation is good. So basically what I can do, I can consider this new partition Q, okay, where this thing is happening. Okay, so I will now I will consider this partition. So in this partition, what is happening, and I apply the bounded variation on this partition. So applying bounded variation to Q. So what we will get, so whatever we will get will be bounded by K. Okay, uh, and that term will have some extra terms. Okay, so in the previous inequality we had summation from 1 to n. So in this we have added how many points? We have added 2n more points. Okay, because each of this is a 1 point, and then how many points? 2n points we have added more. So total number of points will be 3n now. So it will vary from 1 to 3n. Okay, and that summation will be larger than the summation we are having here, because it has more quantity, more positive quantity being added to it, correct? So so in particular what I'm saying is that this summation from 1 to n of f of ci minus f of ci prime, this thing, okay, by n, Yeah. Um, this will be yeah, this will be smaller than I to 3n by these. Let's say I'm writing to be ai minus f of ai minus 1, correct? And now for this, it is smaller than k, correct? So in particular, if I just use these all notations, so in particular, so which will further imply UFP minus LFP is smaller than K divided by N times B minus A, okay, plus 2N B minus A, which is nothing but 1 over N times this, uh, yeah, 1 over N uh, times K plus 2 B minus A. Now these things are constant. Okay, and this 1 over n, I can take n as large as I want, and this will, so as n tends to infinity, this summation will go to 0, correct? In particular, this will be bounded by epsilon. So this completes the proof of that if I start with a bounded variation, it is going to be a Riemann integrable function. Okay, so this completes our discussion on this thing. So this is true. Okay, now let's move on to discuss question number 3. So in this question number 3, uh, again you need to say whether the statement is true or false. You have given a Riemann integrable function, and s and t uh, are two real numbers from this closed interval a comma b. We define fs and we define ft on this closed interval a comma b to r. And the definition of fs and ft are goes as follows. Okay. Now you need to say that fs minus ft is a constant function. Okay. So okay. So so here we are going to use some properties of the Riemann integral functions. Okay. So we have fs of u, fs of x, sorry, fs of x given to be an integral from s to x, correct? And similarly, we have ft of x defined to be x to s, sorry, um, yeah, defined to be t to x, sorry, t to x, f of u to du, and these both of the functions are defined on all of AB. Okay, so if I consider fx, um, yeah, so if I consider uh, minus of ft of x, that means minus of t to x of f of u du. So what happens is, um, yeah, what happens is that the limits are gonna interchange. Okay, so it will be x to t f of u du. Okay, so in other words, what is happening is, instead of taking, instead of going from, uh, so earlier we were going from t to x, okay, from t to x, okay, because your lower limit was t, upper limit was x. If you take the minus sign of it, that means you are going now from x to t. Okay, that's what happens. Okay, So, and now how do we see this property in particular? Yeah. So we use this property, and now when I uh, when I have to find fs minus ft, okay. So this function is going to be defined to be first t to x f of u du minus the integration from t to sorry s to t, and then t to x of f of u du. Now, because now this thing is nothing but equal to, okay, here we again use another property that we can break the integration into parts, into the subintervals of the function. So that's what we have done here. Now you can combine this integration as this. Okay. So this thing. So integration of f of u from s to t, this thing is finite, okay, because f is given to be a Riemann integrable function, okay, and s and t are two variables in this AB. So if it is Riemann integrable on the whole uh, domain, then it is so if you take any point, any subinterval in that bigger domain, it's going to be Riemann integrable in that small domain as well. So we will see this property also today in one of the question. Today, now I'm not going to discuss, but we will see this property as well in the upcoming discussion. So this will be finite because this will be smaller than the integration from AB du, which is finite because this is sub s comma t is a subinterval of AB. Okay, so this is finite quantity. So this is a finite quantity in particular. So it is constant. So this function is a constant function. So that's why it is true. Okay. Okay. Now let us move on to discuss this question number 4. In this question again, it's a true false type question. We have given a function on the closed interval, real valued function, for any constant c, which is positive number, and a t in the real t, which is a real number. We define a function ft, cft, from this interval, closed interval, uh, to r as in terms of the function f. Sorry. So this function fct can be think of as a composition of two functions. Okay, where function g is a linear function. Okay, so you can think of g is a function which is defined to be this, and f is a function which has some definition. Okay, so if you consider the composition, so if you consider the composition of f with g, you get fct. That's what it is. Okay. Okay. And this composition is basically changes the domain. So G is a function from a comma b to a minus t comma c, b minus t comma c. Okay, so if you take x, it goes to ct minus, sorry, cx, sorry. So yeah, my bad. So it is a function from this domain to a comma b, and then on a comma b you have f defined. Okay, so if you take x here, so it goes to c times x plus t. Okay, now x has to be of this form. Sorry, to take t, it goes to ct plus t. So uh, x was fine. This type, and x has to be of this type of form, and you replace these values, you get to ab. That's what the idea here is. The Riemann integration. So we say, so first we prove that this side, again it's an if and only if statement, it can be broken into two parts. First we assume that f is Riemann integrable on AB. Okay, so we assume that f is Riemann integrable on AB. Okay, then we need to show that fct is Riemann integrable on a minus t by c, comma b minus t by c. Okay, so yeah, so for epsilon greater than 0, we need to say that there exists a partition such that the UPF minus LPF is smaller than epsilon. Okay, for given any epsilon, there exists such partition. Okay, so now, uh, so we start with assuming that F has such partition. Okay, so we start with the assumption that F has such partition. So in particular, what is UPF minus LPF? It is nothing but mi minus small mi uh, times xi minus xi minus 1 from I to, so partition of AB, that this is important to note, such that this happens from 1 to n. Now, now the claim is that we say that this partition can also be made a partition of uh, this interval, of the another interval. Okay. Okay. Now, uh, yeah. So we need to find out a partition P prime, uh, which happens to be this. So let us see the images of these xi's under. So now claim is a partition P prime, which is defined to be G of xi for each xi in P, in the partition P, correct? So we say partitions the set. Okay. Yeah. So we say that this partition the set. Yeah. So so it will be nothing but c times xi minus plus t minus c times xi plus 1 plus t. Okay. This will be the uh, difference of the interval. Okay, under that map G. So which is nothing but, if I look at this difference is nothing but, this difference is nothing but C times xi minus xi plus 1. Okay. So if I consider this UPF minus LPF, okay. So now this UPF minus FPF becomes uh, UPFT minus CPFT, because we have changed the interval now. We have changed the interval now. Yeah. Now this is already smaller than epsilon. So this quantity can be, um, so we can choose our epsilon to be epsilon by c, and we can uh, get it small by epsilon. Now if I assume, so this proves that if f is given to be Riemann integrable, then fct is Riemann integrable. Now we assume the second vow, we prove the second part. Now we assume that f of ct is, okay, so f of ct is Riemann integral in this, correct? We start with this assumption. Then we need to show that f is Riemann integral on AB. Okay. So what does this mean? That there exists a partition of A minus T by C, B minus T by C. Okay, so in the previous case, I think there is a mistake. Uh, so we need to start with, we have started with the assumption that AB is a partition of P. Now we need to consider inverse map of G, or a map from A minus T by C to this interval to this. So we have this map G. Now we need to think of a map which is the inverse of G. So in particular, this inverse is simple, which is just y plus T by C. This will be the inverse map. Okay. Oh, sorry. It will be y minus. It will be y minus T by C. Okay. So this will be the inverse map. So and we call this map to be H of y. H will be a map from AB to this. So if I have a partition of AB, then I can make a partition of this interval by just composing it with this map H. Okay, so instead of this, I just need to write H will partition this set, and it will indeed partition the set. Okay, and now what about the maximums in that interval? So whatever the maximum you are having, because the function value is same. So because f of ct uh, of x is same as f of cx plus t, which is nothing but f composed with g of x, correct? It is same as this. Um, so now, yeah. So whatever the maximum of, so or supremum, okay, of this for x in this interval h xi comma h x minus 1. So whatever will be the supremum, let's say this will be mi. Now because this interval, if I plug in this interval, so basically what I'm doing is, if I plug in the values in this, now this is nothing but f composed with g composing with h of x. Now h g compose f, h is nothing but identity, so it is nothing but fx. So this set is nothing but finding out the supremum of f x when x is in xi to xi minus 1. Okay, so the maximum value and the minimum value will remain same. Uh, okay, and then here will be some difference, because this will be xi minus t divided by c. Similarly, xi plus 1 minus t divided by c. This will be divided by c will come up xi minus xi plus 1, correct? And now everything is same, divided by c will appear over here, and then you instead of dividing it by epsilon, you multiply it with c, but this c is again constant, so it doesn't affect the behavior of the limit. Okay, so this limit will still converge to 0 uh, for any given epsilon. So you have found out a partition of this interval. Okay, now, so whatever the argument that I gave earlier was will be suitable for this question when we start with a partition of uh, a minus t divided by c comma b minus t divided by c. So when we start with this partition, so this, let's say this is a partition p of this thing. Okay, and let's say these are the elements in that partition. Okay, so now we consider this new partition q, which is nothing but the images of this partitions. Okay, now if I consider the image of this thing, so this whole interval image will be a comma b. Okay, so these gx I will be in this interval of q. Okay, so this will partition our set a comma b. Okay, now once we have this, again we need to check for the supremums. So mi, so mi is nothing but the supremum of fx, uh, supremum of fx, where x is in this interval. Okay, this might be a bit confusing, so let me just say ct function. Okay, and now this ct function is nothing but f composed with g of x. Okay, and this x is in this, and now this f, if I change the domain, which is if I switch the domain, then this will be just nothing but taking fx from f of gx from this. So the supremum will still remain same. Supremum is not gonna change. Similarly, the infimum are also infimum of fct. Okay, of xi from x in this is will be small mi will be same for infimum of f. Okay, so these things are gonna be same. So again, if I consider the difference of pf, uh, okay, so now if I consider this limit difference, this limit difference will be mi minus mi times the gix minus gix plus 1, 0 to n. Okay, and now what is this? This is just nothing but uh, xi plus t minus xi plus 1 minus t gets cancelled out. You can take c out, and now whatever is remaining, this whole quantity is nothing but c times upf minus, sorry, upct minus lpct. Okay, which is smaller than epsilon for this given partition p. So in particular, this whole thing is smaller than epsilon by c. So this completes your proof. So in particular, you can take your epsilon. Uh, yeah. So in particular, you can take this. You can take your partition P to be in such a way that this thing is smaller than C epsilon. Okay. So you choose your partition P here uh, such that your UPF minus LPF is smaller than C times epsilon. Okay, so that whenever that C comes out, you can cancel it out from this thing. Okay, so it will cancel out, so it will be exactly be this. So it will exactly be smaller than epsilon. Okay, so this completes the proof of the fact that um, yeah. So whenever you have this, when f is Riemann integrable on AB, it is equivalent to say that fct is Riemann integrable on this interval a minus t by c, b minus t by c. Okay. Okay, now let's move on to discuss question number 5. Mm, yeah. So in question number 5, we have two functions uh, from a comma b to r, and g is another function from closed interval a comma b to r, and g is defined to be x plus c. It's a linear function where c is a constant. Again, it's a true and false type question. Uh, it is given that if fx dgx exist, if and only if integral of fx dx exist. Okay. So here gx dgx, you might ask what is dgx. So it is the change of variable. So in the last question also we changed the variable by some linear function. In this question also we are changing the variable of the domain of integration by some linear function. Okay. Now such type of change of variable. So this function is in particular uh, is part of a more general class which is known as monotonically increasing monotonically increasing function. So basically what I'm saying is g is a part of a more general class which is known as monotonically increasing function, uh, and we use this monotonically increasing function to change the domain of integration. And when we do that, then we get a new type of integration uh, where the length of the domain is not the usual length. Okay, so the length of the domain will change by. So in if I calculate this UFP, so it involves the supremum in that interval, in the partition interval, times the length of the subinterval. Okay. Now, if I choose a different, uh, if I take another function g, okay, which is monotonically increasing function, so it changes the this length component. Basically, then it will be replaced by length of this thing. Okay, so it will be replaced by this thing. So this upper sum all denoted by a different notation. So it also involves, it also depends on the function g. Okay, previously it was independent of the length of the interval because we were keeping the g to be the identity map. But when we change our g to some different function than identity, then we need to say mention the dependency of u on g. Similarly, a dependency of L on G, correct? And now this dependency, then again you do the similar definition. Then we similarly define the Riemann integral. But now this integral Riemann integral depends on G, and this integral is known as the Riemann still just integral. Okay, so we denote it by Rg of AB. Okay, so we say a function is Riemann still just integral if UPF g for any epsilon greater than 0, this difference is smaller than epsilon. There exists a partition such that this difference is smaller than epsilon. Okay, so this is another type of integration that we will say. Okay, now basically what this question is saying is that uh, if if my g is given to be a linear function of this kind, and this integration, this Riemann still just integration exists of f, then it implies that the Riemann integration also exists. Similarly, if the Riemann integration exists, then it also implies that the still just integration also exists. So in this case, it is simpler to see, and we will see that why it is happening. So first we assume that that this still just integral exists, dgx exists. Okay, so how do we see that? That means given any epsilon, there exists a partition, okay, of x size xi between a comma b, such that u sorry such that upf g minus lpf g, which is nothing but equal to mi minus mi, xi sorry g of xi minus g of xi minus 1, from 1 to n is smaller than epsilon. Correct? Now, this okay. Now this what is this g of xi and g of xi minus 1? We know that now this thing. Okay, so this is given to us. So let us just keep it clean. Let's say that this is given to us. And now we need to show that we need to find out a partition. Okay, so for some epsilon, for every epsilon, we need to find out a partition. Okay, xi's such that UPF minus LPF is equal to is smaller than epsilon. Correct? Okay, so now how do we say? So my claim is that the same partition will work, the partition we are having in the case of the Stieltjes integral. So let me just use this. So let me just use this given inequality. Um, Now what is g of xi? G of xi is xi plus c minus xi plus 1 minus c. Okay, this is smaller than epsilon. I is varying from 1 to n. And now what is happening is that c is getting cancelled out and you are getting this difference, which is the usual difference uh, we take in the Riemann integral. Okay, so in particular, what you are getting is UPF minus LPF. So in this case, if I just forget about the epsilon part, so in this case, the UPFG minus LPFG is equal to UPF minus LPF. Okay, so what we have observed that UPFG minus LPFG is equal to UPF minus LPF. Okay, so this is what we have noticed. So how do we use this fact? So we will use this fact by saying, so suppose, yeah, now suppose if this part, if left hand side, suppose if this integral exists, that means the left hand side, suppose if this integral exists, that means the left hand side for given epsilon, the left hand side is bounded by epsilon. Okay, which is similar to say that this thing is bounded by epsilon, which is similar to say that this integral, that the Riemann integral exists. Okay. Similarly, if you start with the Riemann integral exists, that means the difference of the right hand quantity is smaller than epsilon, which will imply that it is same to the difference of the uh, Stieltjes integral. Okay, Stieltjes difference, and which is same as to say that the Stieltjes integral exists. Okay, so this is an equivalent statement, but this is very specific to this function because we are taking a very specific function which is Riemann integral function. Sorry, we are taking a linear function which is of type x plus c. That's why this thing is happening. Otherwise, it may not be true. Okay, if we change the function g, then this proof might not work. Okay, this proof is working only because we are taking a special type of G. Okay, now let's discuss this question number 6. In this question number 6, we have again two function f and g defined on ab comma ab to r such that this integral of fx dgx exists. Then it is claimed that f is bounded. So it is again true and false type question. In this case, we further assume that because we are changing the variable, further assume that g is monotonically increasing. Okay, so we assume that because this is a Stieltjes integral, and for Stieltjes integral, we need that g to be monotonically increasing. So we assume that it is monotonically increasing in this question, and then we move on to prove with this question. So in order to say that it is true, you need to prove it. Hello, yeah. Uh, I hope the recording has been done. Uh, I have not noticed that whether I'm audible or not. So let's hope the best. Okay. So yeah. So yeah. Here we assume that f. Sorry. Because we need to because we have still just integral uh, existence. We need to assume that g is a monotonically increasing function. Okay. That's the hypothesis to define. That's a requirement to define the Stieltjes integral. Okay, so we start with that point, and now do we know any example of a function which is not Riemann integrable, which is not bounded? Okay, which is not bounded. So do we know any example? Yeah, we there are multiple example of functions which is not bounded. Okay, so you can because this is because f can be a function which is not continuous also. So you can think of an example which is not continuous and not bounded also. So in particular, when you go towards the 0 or 1, it needs to go to infinity. Okay, and at 0, you can define your function to be 0 or something like that, some natural value. So it is discontinuous, but it is well defined. So what example that I'm thinking of right now is this kind of example. You fix your domain to be 0 comma 1, and you define your function to be like this. Okay, something like this 1 over x type function. Okay, uh, and at 0, let's say you define your function to be 0. So basically, if you think of this function whenever x is non-zero and 0 when x is 0. Okay, so this will be the function that I'm gonna take, and this function is clearly not bounded. Okay, because given any integer, you can find out a value which is larger than that integer. Okay, uh, so this function, so first of all, fx is not bounded. How do we see that it is not bounded? So let's say, uh, so given any n in natural number, yeah. So given any n in natural number, uh, we can take x to be 1 over n. Sorry. Uh, we can take x to be 1 n plus 1 type. Okay. We can take x to be n plus 1. No, this will be, sorry. We take n to be x to be n 1 over n plus 1. Okay. Take x to be 1 plus n plus 1. So what will be g of, sorry, what will be f of x? Now clearly f of x is, this clearly x is non-zero. Okay. So this f of x will be n plus 1, which is clearly larger than n. So you give me any natural number, I can find out an x which is 1 over n plus 1, for example. So that x, f of x, which is 1 over n plus 1, which will be n plus 1, which will be larger than n. So this function is not bounded. Okay. So this is the proof of the unboundedness. Okay. So this is not bounded. First part is fine. Now you need to also come up with a monotonically increasing function, okay, such that this Stieltjes integral exists. So what are the examples of a monotonically increasing function? It is monotonically increasing, which means, so what is the definition of monotonically increasing? So we say a function is monotonically increasing. So we say function is monotonically increasing on closed interval a comma b if you take any two point, which is, if you take any two point in increasing order, let's say x and y, where y is greater than x, then their corresponding function values is, uh, needs to satisfy this inequality. They needs to be, the value of g of y needs to be either equal or greater than g of x. So in particular, you can take constant function. Okay. So constant functions are monotonically increasing. Okay, because they are always equal to, uh, because they are always, uh, yeah, constant functions are one of the example, because for any xy, f of x will always be equal to f of y. Okay. So this is an example of a monotonically increasing function. uh, yeah, other example could be linear function and so on and so forth. Let's not go into that. Identity function is another example of the increasing function. So let's take the simplest example, which is the constant function. So okay, so g, better to use g over here. Okay, so we take g from a to b to r, which is x going to constant c. Okay, hope c is not used anywhere else. Okay, so g is a monotonically increasing function, and now we say that now we need to claim that this still this integral exists. Okay, we need to claim this. So how do we claim this? So we say that for given any epsilon greater than 0, there exists a partition such that, so there exists a partition xi from ab such that this difference is smaller than epsilon. Okay, this difference is smaller than epsilon. Okay, sorry, yeah, there is, because we are talking about still just integral, so there is part of g is also involved. Okay, this is smaller than epsilon. Yeah, so now what is ufg? So what is pfg minus this thing? It is nothing but the difference of supremum infimum times the length of the interval. Now in this case it is g of xi minus g of xi minus 1, correct? Now what is gi of xi? It is c. Again this is also c, so c minus c, mi minus mi. Now this is going to be 0, because 0 times 0 something is 0. Okay, So this is gonna cut. So this is going to be 0. So this 0 is always smaller than epsilon, for because that's what the assumption, that you are starting with a positive epsilon, so it has to be greater than 0. So this implies that this exists. Okay, that means this is still, this integral exists, but but uh, yeah, but this f, yeah, but this f is not, um, yeah, yeah, but this f, uh, which is 1 over x, is not bounded. Okay, so this statement is false. Okay, so we have come up with an example of function f which is not bounded, but the Stieltjes integral was existing. Okay, so this question number 7 is a bit lengthy, so I will discuss this question in the next session, not today. Okay, so let me see if there is any short question which we can discuss. This is also short. This is short question. This can be discussed. Uh, this question can also be discussed. It's also a short question. Um, okay, this function is also seems to be small. So what I will do, I will discuss the question number 8, and then see. Let's see then how much time do we left. We only have 15 minutes, or less than that. Okay, so let's discuss this question. I hope the last question was clear to all of you. If it's not, you can comment it down uh, in the video. Okay. Yeah. So this question says that f is a continuous function on a closed interval and it's a real valued function, and it also takes the positive value. Okay, positive or zero value. And further, it is given that the integration of f on this closed interval is 0. So now the claim is that this f is going to be 0. Okay, so we will try to prove this. It seems to be the true case because the integration is always the uh, integration is, because we are integrating a positive function, so it has to be positive. Okay, so yeah, so we use that intuition to prove this part. And how do we do that? um, we also notice that it is a continuous function, so because this continuity will be required in the proof. Okay, suppose if it's not continuous, uh, so then if I drop this hypothesis, then can you generate a function uh, who is going to be positive or zero? An integral can be zero, uh, but then the function is not non-zero. So a hint can be, so what I'm saying is, uh, let's drop continuity continuity of f. So what do we get? So do we have any example? Yes, we can. Just think of this example where you define your function to be, this is, let's say, 0, this is 1, and this is 2. So you have a function defined from 0 to 2 to r. Okay, and you define your function to be, it is 1 when your x is in this 0 to 1, and it is -1 when it is, oh, you want it to be positive always. Oh, it is either positive and So yeah, yeah. So the best example can be you just take at a random point, for example, at zero, or let's say for at one, you take this to be one, and rest of the point at rest of the interval it is zero. So zero for x uh, for x not equal to one, and one for x equal to one. Okay, so this function is not continuous, but the integration of this function will be uh, zero. Okay, and this function is also not does not satisfy this inequality, because at one it is oh sorry, this function also satisfies this inequality because uh, it is always positive or zero. It is either positive or zero. Okay, so this function also satisfies this equality, but it is not continuous. Oh, sorry, it is not continuous, and its integration is zero, but the function is not zero. So this function fx is not zero completely, because at x equal to one, it is non-zero. Okay, so this is so if we drop the continuity, we can construct infinitely many examples where this function need not to be zero. But so that's why the continuity plays an important role in proving such questions. So that's why we can't drop the continuity from this question. Okay, so let's solve this question. So we know that this integral is bound between the this integral bounds between the lower sum and the upper sum. Okay, it's sandwiched between them. So for epsilon greater than zero, one can find out a partition P um, such that such that UPF or LPF will be important in this case. So LPF, oh UPF, yeah. Oh, we don't even need to go to the existence of epsilon. We can just say that. Uh, so this is true for any partition, correct? This is true for any partition P. So let's take a partition. Let's fix one partition uh, of AB to be A naught to be X, A to be X naught. Uh, yeah, partition of I times B minus A by N, where I is varying from 0 to N, correct? Yes. So we take, if I take this partition where I divide my interval in some uh, uniform length in subintervals. Yeah. So if I do that, so what will I get? LPF is what? It is nothing but minimum times the difference of the subinterval, which is in this case it is B minus A by N, and you sum it out all over uh, the number of partition, and it uh, is smaller than this value. Now this, because F is continuous, okay, on AB, there exists xi, sorry, there exists some ai in this interval such that mi is attained by this ai, okay, by the function, and this is given to be greater than or equal to 0. Okay. So now we further, so what do we get from here? We get that f of ai, uh, this summation b minus a by n is uh, larger than equal to this. Okay, now if we assume that f is not zero, okay, and since f is positive or zero, this implies that f is positive, strictly positive, okay, on AB. So what does this will make us? What does this reduce this star equation to? That we have this thing of ai from 1 to n, b minus a divided by n, uh, equal to this integral. Now this whole quantity is positive. Okay, this each term is positive. Similarly, this thing is also positive. So this thing is positive, strictly positive, which implies that integral of f is positive, which is a contradiction to the assumption, which is a contradiction to the hypothesis. Okay, so in the hypothesis we assume that the integral is zero, but it is saying that it is going to be positive. So uh, yeah, so it is a contradiction. That means the assumption we made over here must be wrong. So this assumption is wrong. That means f has to be zero. Okay. Yeah. So basically, yeah, I just realized that this this implies um, this implies that f of x has to be zero for some point x in the interval. Okay. It doesn't say that um, x has to be uh, zero on the complete domain. So we need to do some extra work still to prove that it is a zero in whole of whole of x, a whole of the domain. Okay. So I leave that part to you guys to think of. Okay. Um, if it is not clear to you, we can discuss it in the next discussion as well. Uh, yeah. So we stop at this moment. So we will meet next week. Recording will be available on the YouTube channel, Maths with Prerak. You can go and check it out. Uh, okay, bye everyone.